Okay, well, welcome to Lecture 3 of Math E102. I want to start with a couple of announcements that concern both the people in the classroom and distance learners. First, about finding the videos. I had been getting at the videos through the faculty interface to the extension website, and I had no problems. And it was only when a couple of you had the foresight to email me that I realized that the page on which the first lecture was readily accessible didn't have the second one. I have now, I think, put a good link on the homepage of the course website, which is the easiest way. So I want to check, is there anyone here who has been trying to get at last week's lecture and still been unable? Okay, and just out of curiosity, are there people here who looked at last week's lecture on video? Oh, well, that's not bad. So there's a side benefit to doing this for distance learning. The second thing is, one might reasonably say that unavailability of textbooks and difficulties at getting at the video might have caused some people not to get their homework done on time. And I think this is a reasonable way to deal with this. You folks are adult learners. You have families, you have jobs, you have all sorts of things that mess up your schedule. So let's just say 3 times during the term you can turn in your homework a week late if you feel like it, and we're not interested in your excuse. And if you do it a 4th time, we're not interested in your excuse because we don't care how good it is. So hold on to these, but when something comes up, turn it in a week late. Chris will keep count, and as long as you stick with 3, you'll be fine. And at the end of the term, we will have a mechanism for, in effect, throwing out the lowest homework grade. The way we usually do this is by turning one grade into a perfect grade in a manner that benefits you the most. So I suppose that might make up even for a 4th late assignment. Oh, that's late. Yeah, we were really tough. Before I get started, any issues or questions regarding the course or the way it's run or anything, or comments? Any comments from people who've looked at the lecture? I got one email saying, on the first lecture, I couldn't hear the questions from the class. Last week, things were much better, and did you put an extra microphone out there? I certainly didn't, but maybe someone did. Another?
No, that was my comment.
Oh, you're Sue?
Yeah.
Oh, okay. Yeah, that was very helpful. So anything like that, I know the most important thing about being on video, which is don't wear checked shirts. But if there are things I might reasonably change to make the lectures better, let me do so. Okay, tonight we're basically going to do nothing but organized counting. So now I want to get on to topic number 1, called count a Cartesian product. This is going to be proving something that's so obvious that you might not think it was provable. And I'm doing this mainly as a very elementary example of a proof by induction, where you go from the case n equals 2 to the case of arbitrary n. So suppose you get hired as a wait person somewhere. This is a restaurant that doesn't serve soup, so you only have to put out a knife and a fork. And we have m knives, 1 through n, and n forks, 1 through n, and your boss says, pick a knife, pick a fork, put it out at that place on the table over there. And the question is simply, how many ordered pairs of knife and fork do you have to choose from? And the answer is, you could pick knife 1 and fork 1, knife 1 and fork 2, on up through knife 1 and fork n, or you could pick the mth knife and the first fork, or the mth knife and the n fork. And clearly, there are m n ordered pairs. And I think in most people's mind, this is what the definition of multiplication of integers really is. Technically speaking, you're counting the size of the Cartesian product of two sets, the set of knives and the set of forks. Now, time and again, we will be using this same formula, but where we have a large number of different alternatives. And so what I want to do is consider the general case, and now I'm going to change the meaning of n. N is going to be the number of different types of objects that we have. So we've got type 1, which might be a fish fork, and C of 1 different fish forks, and type 2, which might be a salad fork, C of 2 salad forks, and we might end up with type N, which is the dessert spoon, and C of N different dessert spoons. And what I want to prove is the obvious formula that the number of ordered n tuples, is, of course, C of 1 times C of 2 on up through C of n. And the obvious way to prove this is by induction. And here's my base case, isn't it? We already have this for n equals 2. Okay, now here's the way you want to think of this for the inductive step. You think you've got everything set up, and the chef comes out and says, we're serving gourmet pickles tonight, and we have to put a pickle fork at every place, and we have C of n plus 1 different pickle forks available in our pickle fork cantina. And you ask, oh, how many different place settings are there now? And you argue, well, for what we've already got, I can assume that this formula is correct. And now I want to prove that the same formula is correct if we have n plus 1 species of cutlery, including the pickle fork. So the inductive step looks like this. We say we can assume that we've already got C of 1 times C of 2 up through C of n, different possibilities for the first n types of utensils. And then using the base case, since we're combining any of those with one of the C of n plus 1 pickle forks, this is the number of possibilities with n plus 1 utensils. And this checks out, and that completes the proof. So really, from the definition of multiplication, as far as I'm concerned, the n equals 2 case holds, and we can extend this, and this is the most important principle of counting. So now I'd like to enumerate the others, which means we're going on to topic number 2, principles of counting. While I'm on this, those of you who watch the lectures, is the number of topics about, how many of you have actually used the topic list to flit around in the lectures rather than just watching from beginning to end? Okay, one person, so this is moot. Anyway, if anyone thinks there are too few topics, it would be possible to subdivide some of these. That is, if you're trying to find something and you have to watch 5 minutes of something that you are already thoroughly familiar with to find it, I can break this up a little bit finer. Okay, so now we'll go to counting principles. I've listed 4 of these, and the first 2 are extremely important. The third and fourth are of less general utility, but still nice for solving homework problems. So, number 1, I'll list as multiply for sequential counting. That is, if you're making a sequence of choices and you want to figure out how many tuples of choices there are, just multiply together the number of choices you have at each stage. The second one is a little bit more subtle. sometimes when you do this, you know you're counting things more than once. And a lot of people, on realizing that, say, I'm doing this problem wrong. I'm going to have to go back and start over. And in fact, a lot of the time, you are overcounting by precisely the same factor for each case. And in that case, you just go ahead and overcount and divide out by the number of times you overcount. So I'd like to illustrate this with a simple example on the overhead screen, if we can get that up here. Okay, here I have a diamond suit, and I propose to shuffle this and select a hand of 5 diamonds out of this suit. Now let's think about how I do this. Out of my deck, I pull a card. How many choices do I have? 13. Okay? Now out of the remaining cards, I choose another. How many choices this time? 12. And then 11. And then 10. And then 9. So for a start, I have 13 times 12 times 11 times 10 times 9. And that's the correct count for the number of different 5-card sequences you can pull out of the 13 cards in the suit. But that's not what card players do. What do? I pick this up. And I probably arrange it so that the cards are in ascending order like that, don't I? And then I look at it and see what I've got. I might at that point ask whether the 5 cards are strictly in sequence, like 2, 3, 4, 5, 6. So the question now is, how many times have I overcounted each of these hands? How many different ways can this collection of 2, 3, 6, 8, and queen arrive? 120, sure, because there are 5 factorial ways of arranging those cards. So I have to divide this by 5 times 4 times 3 times 2 times 1. And here is an efficient way of writing this. 13 factorial, of course, means 13 times 12 times 11 on down to times 2 times 1. Since I stopped at 9, I have to divide by 8 factorial in order to quit here. And then I've got this 5 factorial in the denominator. And this particular collection of factorials, where the number in the numerator is the sum of the 2 numbers in the denominator, shows up so often that it's been given a special symbol and a special name. 13, choose 5. And this is called a binomial coefficient. And I should also say, this is also equal to 13 choose 8. That is, I could choose the 8 cards that are not in the hand and have the same effect as choosing the 5 that are in it. Last week I didn't use these things at all. We did a lot of interesting counting, and the big difference between last week and this week is tonight pretty much everything is going to be based on counting and probabilities based on counting, where we use binomial coefficients to organize our counting. And I hope things will seem quite a bit easier. Last week, there were a number of problems that were rather ad hoc, and you had to be pretty clever in your counting. And I think when you're using binomial coefficients, you can be considerably more systematic about it. Now, there are 2 other principles I want to list, and you will need these from time to time. The third one I've called divide and conquer, but it really concerns counting a disjoint union of sets. And I'm going to give an example from poker. Now, this is always risky How many of you have never in your life played poker? Okay, so you don't know a flush from a full house, huh? Well, you better buy a copy of Hoyle's Rules of Card Games. When teaching introductory computer science once in the extension school, I had this brilliant homework assignment involving counting up hands and figuring out who won the poker game. And my students were great at coding in Pascal, but it turned out half of them didn't understand the rules of poker well enough, and I had to pass out the entire set of poker rules from Hoyle's Rules of Card Games in order for them to complete the assignment. So, Anna, this won't make much sense to you, but it may for the other folks. There are variants of poker where in order to make the first bet, you have to have a pair of jacks or something better. And a reasonable question is, what's the probability that an individual will hold a pair of jacks or something better? If that isn't substantial, then there's a risk that very frequently the game will be rather a flop because no one will be able to bet. And the way to figure that out, probability of 2 jacks or better, is by adding up the probability, maybe I shouldn't say probability since we're counting, I'll use n, the number of different poker hands that have 2 jacks or better is the number with a pair consisting of 2 jacks or better plus the number of hands with 2 pair plus the number of hands with 3 of a kind on up to plus the number of hands with the straight flush. And there's really no shortcut on this. You have to do all these calculations and add them up. So from time to time, you'll end up with a messy situation where you just have to say the type of set for which I want to do the counting is a union of many different disjoint sets. I'll count those individually and add them up. And the last one, which is relevant to the homework, is to subtract off special cases. And what that means is from time to time, you will have the difference of 2 sets. And a good way to count the difference of 2 sets, A take away B, is to count A, count B, and subtract. Here is a slightly complicated example from poker. I passed out Durango Bill's, oh, this isn't really difficult. I passed out Durango Bill's poker pages off the web, and I will be replicating some of those results shortly, and you will be replicating others for homework. And one where people have enough trouble that they send me email about it is when I ask them to replicate Durango Bill's count for the number of hands that qualify as a flush. Now, would an experienced poker player like to provide a definition of flush? Yeah, Jerry?
5 cards all of the same suit.
Wrong.
5 cards all of the same suit. It's not a straight flush.
Very good.
Oh.
It's only a flush if the 5 cards are all in the same suit, but they're not in sequence, because if they're in sequence, they count as a straight. This slowed me down for about 15 minutes the first time I tried to replicate the Durango Bill web page. So that means if you want to get his count on the number of flushes, first you have to count the number of cases where there are 5 cards of the same suit, and then you have to subtract off from that the number of hands that qualify as a straight flush, because a straight flush beats even 4 of a kind and is not regarded by poker players as a species of flush. Okay, before we get to poker, let me explain a little more about binomial here. and reproduce the best known case of the binomial theorem by a counting argument. So we're now on to topic 3, which is called binomial theorem. This is not by any stretch of the imagination the most elegant proof of this result, but I like it for tonight because it's a pure counting proof. A bit of mathematical history trivia. Anyone have an opinion as to who first proved the binomial theorem in general? Yeah, that's what I thought too. So Jerry guessed Newton, and I think Newton did prove this case, but I believe that in the general case, which we won't be needing, Newton conjectured that the result was true and used it in an ingenious way of calculating about 12 decimal places of pi, but he wasn't able to prove it, and the proof was done about a century later by Euler. And in fact, Euler's proof involves some fairly fancy single variable calculus. So we're not going to be doing the general case, which is hard. We're going to be doing the simplest case. We want a formula for 1 plus x raised to the nth power, where n is a positive integer. This is the one you learned in high school, and this may be the proof you learned. What does this mean? It's 1 plus x times 1 plus x times 1 plus x, and so on, times 1 plus x. And there are n factors here. And what would your average 8th grader do with it? Well, the answer is multiply it out. So you start enumerating all the terms. And the first one you get is 1, 1, 1, 1, 1, where you use all the ones. And then there's going to be a term where you have 1, 1, 1. And the last one is an x, and maybe 1, 1, 1, ending in an x, x. And at the very end, you'll have a term with all x's. And in all, there will, of course, be 2 to the nth power terms. Now, of course, you want to combine these, because a lot of them are the same. Anything with 1x just contributes to the term that has x. Anything with 2 x's contributes to the term that has x squared, and so on. So let's ask, what is the coefficient of x to the k? And the answer is the number of terms like this. It will be a mix of 1s and x's. That's just a representative mix of 1s and x's. And in this mix of 1s and x's, there will be how many symbols?
Yeah.
Either a 1 or an x is a symbol. If I take these factors and multiply them together, there are going to be n symbols. And of those n symbols, how many x's?
Okay.
And sorry, I'm going to fix this. My wife and I play Scrabble from time to time, and I maintain that XS is a valid word, the plural of the letter S. And now, I don't want her going to the website and say, look, Paul, you spell that X apostrophe S, you can't play that. So we've got n symbols, including k x's. And so how many terms are there like that? How many ways are there of arranging n symbols of which k are x and the remaining n minus k are 1?
N choose K.
N choose k. Everyone comfortable with that? That's how you count how many terms there are, where when you add up the exponents of the x's, you get a k. So now we know there are n choose k terms that have k x's in them, and we have the answer. Is this still coming over the screen? Is this visible at this height? Good. So 1 plus x raised to the nth power is the sum from k equals 0 to n of n choose k times x to the k. And that's why this symbol is known as a binomial coefficient, because it's the coefficient of x to the k in the binomial expansion 1 plus x raised to the nth power. Okay, now we can do poker. So I'm moving on to topic number 4, poker hands. And I have brought along numerous decks of cards tonight. And this one is the absolutely standard deck. It's all mixed up, but I'll shuffle it nonetheless. And we're just going to play two-handed. And I don't care what you get. The point is, here is a sequence of 5 cards that came out of this deck, and any sequence of 5 out of the 52 cards, I assume, is equally likely. If the sequences are not equally likely, the dealer did a lousy job of shuffling the deck. So, let's count the number of sequences. The number of 5-card sequences is 52 times 51 times 50 times 49 times 48. Bear with me for a minute because I'm going to pick up my hand now. Oh dear, I fold. Well, I look at this. I might arrange the cards in order. If I were lucky enough to have 2 7s, I'd put the 2 7s together. But anyway, as a poker player, I have a systematic way of arranging my cards, and I completely destroy the history of how those 5 cards showed up on the table. So as before, there are 120 different sequences of 5 cards that, as far as I'm concerned, all correspond to exactly the same poker hand, and therefore the number of distinct hands is this number. I'll write it out one last time. Divided by the number of ways of arranging the 5 cards in the hand. And this is, of course, 52 factorial over 5 factorial times 47 factorial, or 52 choose 5. This is a rather large number, which I will write down a couple of times. It's actually 2,548,960, which you can find on Durango Bill's webpage or in numerous other places. And in fact, all of you, whether in the classroom or watching on video, might as well go to the Durango Bill handout. There's a bridge one and a poker one, because I'm going to be trying to reproduce some results from Durango Bill's webpage. So we'll go to Durango Bill's webpage. And I don't see any copyright notice, so I think this is legal. So this is what I want you to be looking at. This number of combinations is his count, which is actually thoroughly correct, of the number of distinct hands that fall into each of these categories. And the probability is obtained, of course, just by dividing that by 52 choose 5. The probability aspect is very minor tonight. It's the counting that's the hard part. So let's go for the first one. 4 of a kind. Okay? 4 of a kind. You could have 4 aces, or 4 eights, or 4 twos. And what we want to do is basically to figure out how many choices we'd have to make in order to enumerate all the possible 4 of a kind hands and multiply them together. So if we wanted to stack the deck to produce a 4 of a kind hand, how many choices are there for the rank of which we get 4 cards?
13.
13. Okay, now we've got our 4 of a kind. How many ways are there to fill out that hand to make a 5-card poker hand?
48.
Wait, what's the 13?
The 13 is I could have 4 twos or 4 threes or 4 aces. I could have 4 cards of any of the 13 ranks. Okay, so I've now got my 4, but I need a 5-card hand. Having selected 4 cards of one rank, how many choices are there for a card that will fill out the hand to make it 5 cards?
48.
48, right? Because any of the other 48 cards in the deck will work. There is no 5th card of the same rank, so anything else will do. So that means there are 13 times 48 ways of getting 4 of a kind, and the probability of 4 of a kind is therefore equal to this product, which I believe is 624, divided by 52 choose 5. And if you look at Durango Bill, you discover that he's got the same number, and he's got this probability over here. By the way, Anna, if you've never played before, this knowledge will do you very little good as a poker player. Skill in poker playing is mainly in the bluffing. You need to know these probabilities, but I'm great at probability and I'm lousy at poker. Okay, let's try a couple more. Next one I want to do is a full house. And for those of you who engage in clean living and are unfamiliar with this, a full house is the term applied to a poker hand where you have 3 cards of one rank and 2 cards of another. So 3 queens and 2 eights would be a full house. And by the way, one of the principles of poker is the cards speak for themselves. So if you lay down 3 queens and 2 sevens and say, I've got 3 of a kind, your opponents are obligated to say, no, you've got a full house and you win. Okay, let's try this. Full house. You're stacking the deck to deal yourself a full house. The first thing you do is to pick what 3 of a kind you get. How many possible ranks are there for the 3 of the kind? 13. But now it gets a little bit more subtle because you're only choosing 3 of the 4 cards. How many ways are there to select the suit for your 3 of a kind?
4.
4. And if you want to be fussy, you write that as 4 choose 3. If you want to be quick, you say, yeah, I can leave out the spade, the heart, the diamond, or the club. Okay? So now you got 3 cards. The last 2 have to be a pair. How many choices are there for the rank of that pair?
12.
12. Because you can't duplicate the one you've already got. And how many ways are there to choose the suits that are involved in that pair?
6.
6, okay? 4 choose 2 or 6. Okay, so the probability of a full house is therefore 13 times 4 times 12 times 6 over 52 choose 5. And when I multiplied out the numerator, I got 3744. And when Durango Bill multiplied out the numerator, where did Durango Bill go? Yeah, he got 3,744 too. Now, don't get overconfident. The next one I actually once did wrong in public. So I'm now going to do one that's a little bit tricky, and so are the ones on the homework. I want to do 3 of a kind. And Jerry, since you got burned on the flush, you want to define 3 of a kind for us?
3 of one rank and 2 cards that do not form a pair.
Very good. So 3 of a kind in poker is 3 cards of one rank and then 2 other cards that are not of the same rank as one another and, of course, not of the same rank as your 3 of a kind. But we're organized about our counting, so we're going to get this right on the first try. 3 of a kind. How many choices for the rank of which we have 3? 13. And as before, 4 choose 3, or 4 choices for the 3 suits we've got, or the 1 suit we have left out. Now let's think about the rest. And here's the way to do it and get it right on the first try. We've got a pair of other ranks, right? There are 12 other ranks, and we need to choose a pair of 2 different ranks for the remaining cards. How many pairs can you make out of 12 different ranks? How many pairs of ranks? Or if I may ask the question very baldly, how many ways are there of selecting 2 ranks out of the remaining 12?
12 times 11.
12?
Times 11.
No.
Divided by...
Let me use a different verb. How many ways are there, hint, hint, choose, of choosing 12 ranks of the remaining 12? 12 choose 2.
Which is 12 times 11.
And that fixes the error I made. You notice that's not 12 times 11. Because if your remaining ranks are, say, an 8 and a 6, choosing a 6 and an 8, choosing an 8 and a 6, both leads to the same hand. If you use binomial coefficients like this, you get it right on the first try. The binomial coefficients have already corrected for overcounting. So if you suspect you're going to overcount, if you use binomial coefficients, that will do the correction automatically. Now, there's one more remaining subtlety. We've chosen our other 2 ranks. How many combinations of suits are there for those 2?
Choose 3 for both of them.
6.
No, wait a minute. We've got 2 other ranks. Like we're filling out our 3 aces with a 9 and a 7. How many choices for the suit of the 9?
4 choose 3.
4. And then how many for the 7?
4 choose
4. No one cares if you got 3 of a kind, whether your other 2 cards are both spades or not. So we've got times 4 times 4. And when I multiply that out, that's 13 times 4 times 66 times 16, which, lo and behold, works out to 54,912. And if you look at Durango Bill, he's got 54,912 also. If you get inspired and try to replicate all of Durango Bill's results, the one that might give you the hardest time is the one at the bottom, which is called high card only. This means a hand that doesn't qualify for anything else, and its only chance of winning the pot is based on the highest card of the hand. And what I did was to throw into the Windows calculator the following. I said, well, there are 52 choices for the first card, then 48 if I don't want to match its rank, and 44 that don't match the rank of anything that preceded, and 40 that give me another different rank, and 36. And these can come up in 5 factorial or 120 different orders. And when I did that, I got 1317888.
You didn't take out for flushes?
For flushes.
Oh, yeah, you catch on quick. And, of course, this is wrong. It doesn't agree with Durango Bill's because what I forgot was that I have to subtract off special cases. Of the hands that have no pairs whatever in them, there are 3 special cases. There's the straight, where the 5 cards are all in sequence, and the flush, where the 5 cards are all in the same suit, not to mention the straight flush, where all cards are of the same suit and in sequence. And what do you know? When I subtracted off those, I got precisely the answer on the Durango Bill webpage. A royal flush is a straight flush consisting of 10, jack, queen, king, ace. And since straight flushes are ranked against one another, according to the highest card, I think it would be interesting to estimate the probability that in the entire history of poker playing, there has ever been a showdown where two different players had straight flushes, and this had to be used of different suits. Yeah. You know, I've got the 9, 10, jack, queen, king of hearts. Well, tough luck. I've got the 10, jack, queen, king, ace of spades. So give me the deed to your ranch and all your cattle, and I'll ride out of town.
There's been so much poker played, I wouldn't be surprised if it didn't happen a few times. There have been billions and billions of poker hands.
But the probability of one straight flush is 0.00001. Okay? Square that roughly. Now, it's true that if one person has a straight flush, the probability that someone else has a straight flush is probably a teeny bit higher. So that means we got 10 zeros and a 1. We're talking 10 billion. So this situation with different players in the game might occur once every billion or so. It's probably happened a few times in history.
They play straight 5-card draw.
Oh, that's true. That's true. Yes.
Without any...
Yeah. Okay, well, let's go on to bridge. And I think I put on... Yes, I did. Problem 5 on the upcoming problem set. Yes, it is on the upcoming problem set. This is a true story. No, this is on next week's problem set. Okay, but since bridge is coming up now, I'll tell it to you now. I only play bridge when on cruise ships. And my wife and I were cruising on the Grand Princess, and it turned out they had a couple that was running quite competent duplicate tournaments on the ship and giving lectures. So I went to the lecture, played in the duplicate tournament, made friends with the wife, and she said, "What do you do?" And I said, "I teach math at Harvard. I teach a probability course." "Oh, you ought to sign up to give lectures on cruise ships, and then you can cruise for free." And I thought, that's the stupidest idea I've ever heard, but I didn't say anything. So I thought about this, and the next day I went back and said, "You know, Marsh, I've been thinking about your idea, and let's give it a try. I noticed you've got a lecture scheduled for tomorrow, and unless you've got a topic you're just burning up to talk about, why don't I give a rigorous proof that holding 9 cards of your trump suit and missing the queen, you should lay down the ace and king rather than taking the finesse?" And she said, "Well, that sounds good." And so all these folks wandered into the bridge room and sat down. She introduced me. I got up at the easel and in 20 minutes did a perfectly rigorous proof, which I based entirely on counting. That is, I didn't introduce the concept of probability, which is rather difficult. Instead, I hypothesized that there were so many ships in the Princess fleet that when they played duplicate bridge tournaments, they could set up this hand, and each way of distributing the remaining cards between east and west occurred on one and only one cruise ship. So if you picked up your hand, you could look at this and say, well, how are the other cards distributed? I know that on 12 million of the sister ships, they are distributed this way, whereas on 10 million, they're distributed in the way that this play will lose, and therefore this play will win on 12 million out of 22 million cruise ships, and it's the right thing to do. And people seem quite happy with this. So happy, in fact, the last cruise I went on, I gave the same lecture all over again. But nobody's offered me a free cruise yet, so don't push it too far. Okay, so now getting started with bridge. How many of you are totally unfamiliar with the rules of bridge? Oh my goodness. Okay, so I got to tell you just a little bit about bridge.
No money in it.
It's master points. That's worth more than money. So, The only thing you need to know about bridge is all the cards are dealt out with the effect that everyone ends up with 13 cards, and I'm only interested in one of these hands. So I pull out my hand, and I generally arrange it so all the spades are together, and then all the hearts are together, and all the clubs are together, and all the diamonds are together. And in thinking about how I might bid this hand, probably the first thing I notice is this is a moderately balanced hand in the sense that there's no suit longer than 5 cards and no suit shorter than 1 card, but it's not wildly balanced. It's not balanced enough, for example, so that I'd consider bidding no trump with it. So bridge players pay a lot of attention to the distribution of the cards among the different suits. And a bridge player, on looking at this particular hand, would say, I have a hand with 5, 4, 3, 1 distribution, which means I've got 5 cards in my longest suit, 4 cards in my next longest suit, 3 cards in my third longest suit, and 1 card in my shortest suit. So what I would like to do is work up to counting the number of bridge hands with, for example, a 5, 4, 3, 1 distribution. But we have to do a simpler case first. More significant about this hand is that it has 5 hearts, 4 diamonds, 3 clubs, and 1 spade. So let's calculate the number of hands with a specific suit distribution. And since I put it in the notes and I've done the arithmetic, let's count the number of hands that have 6 spades, 4 hearts, 2 diamonds, and 1 club. But from my illustration up here, you get the example. You get a sense of why this issue arises in practice, right? Okay? A good way to answer this question is if you wanted to lay out a hand for teaching purposes with this, you'd have to reach into the 4 individual suits and pick out the cards. And how many ways would there be of selecting the 6 spades that went into the hand? 13, choose 6. And how many ways of selecting the 4 hearts? 13, choose 4. Anyone want to guess how many ways of selecting the 2 diamonds? 13, choose 2. And then, of course, 13, choose 1. So that's really, really easy. What is only slightly more difficult is the number of hands that have so-called 6, 4, 2, 1 distribution, by which I mean 6 cards in the longest suit, whichever that may be, 4 in the next longest, and so on. And how many cases of this type contribute to this? That is, how many different ways are there of assigning the 6, 4, and 2, and 1 to different suits? 4 factorial, right. How many choices for the longest suit, Sue?
4.
4. And then for the next longest suit? 3. Everyone got it? So this is 24 times the number of ways of getting 6 spades, 4 hearts, 2 diamonds, and 1 club. And if you put those numbers into a calculator, you will replicate the number that is on Durango Bill's bridge page. I don't want to do this calculation because it leads to a big, meaningless number. I want to do one calculation like this in order to show you how easy it is to work with binomial coefficients if you cancel first and expand later. So here is the puzzle that I want to explain. I learned bridge when I was in junior high school, and I read various theoretical treatises on the subject, and I got the general idea that balanced hands were more likely than unbalanced hands. And I figured, well, the most balanced hand is 4, 3, 3, 3, right? 3 cards in each suit plus 1 extra. And then when I read that the most frequently occurring suit distribution is 4, 4, 3, 2, I, being a naive 8th grader, thought, how could that be? That's not the most balanced sort of hand. But it is, in fact, the case that 4, 4, 3, 2 is slightly more than twice as likely as 4, 3, 3, 3. And the one bridge calculation that I want to do is to explain why this is so. And I should warn you, this sort of calculation leads to nice quiz problems. This is a little more difficult than your typical quiz problem, but the style of it is worth learning how to emulate. So let's first figure out the number of hands that have 4, 4, 3, 2 distribution. And you got most of the idea. This is 13 choose 4 times 13 choose 4 times 13 choose 3 times 13 choose 2. And the hard part is the coefficient outside. With 6, 4, 2, 1, we had a 24 outside. What do we have outside this time? No? Look at it this way. I say, partner, I have 4, 4, 3, 2 distribution. Ask me a couple of questions to find out more about my hand. What's the first question my partner might reasonably ask me? What suit do you have only 2 cards in? Okay? And how many possible answers are there for that? 4. Okay? And then my partner says, okay, then which suit do you have the 3 cards in? How many answers are there to that? 3. And then my partner knows everything about my suit distribution, right? Because the other 2 suits are the ones I have 4 cards in. So we multiply by 12. Another way of doing this, you can say there are 24 ways of arranging the suits, but that counts the 4 hearts and 4 spades case twice because it will count hearts, spades, and it will also count spades, hearts. Okay, so this 12 is the crucial thing. Now, I'll write down the obvious while you think of the multiplier. 13 choose 4, 13 choose 3, 13 choose 3, 13 choose 3. And this is the number of ways of, say, getting 4 spades and 3 cards in each of the other suits. What do I multiply by? 4. Because the only thing unknown about this is which suit do you have the 4 cards in. So it is true for specific assignments of number of cards to suits, this is more likely than that. But when you add them all together, this factor of 12 trumps the other ratio. So let's get the ratio. N 4, 4, 3, 2 over N of 4, 3, 3, 3. And here's how we're going to do it. Here's what you don't do. With a calculator, this may not be so bad, but by hand it's terrible. Don't multiply all the factorials out. Instead, cancel as much as you can. So we've got 13 factorial over 4 factorial times 9 factorial. The same thing. 13 factorial over 3 factorial times 10 factorial. And 13 factorial times 2 factorial over 11 factorial. And then in the denominator, I have 13 choose 4 again. And that cancels that. That's a really good start. 13 factorial over 3 factorial times 10 factorial. 13 factorial times 3 factorial over 10 factorial. That cancels that, which is major progress. And 13 factorial over 10 factorial times 3 factorial. Okay. Now, that cancels that, cancels that, and now we're making real progress because in the numerator we now have 10 factorial times 3 factorial times 10 factorial times 3 factorial, whereas in the denominator, we have 4 factorial times 9 factorial times 2 factorial.
You're missing the 12 over 4.
Ah, I'm missing the 12 and the 4. 12 there, and 4 there. So I have 3 times that. Okay, now let's simplify this. What's 10 factorial over 9 factorial? 10. So we've taken care of those. We've taken care of that. What is 3 factorial over 2 factorial?
3.
Taken care of those. What in the denominator is 11 factorial over 10 factorial?
11.
11. And 4 factorial over 3 factorial?
4.
4, which is 90 over 44, or 45 over 22. So this type of distribution is more probable by roughly a factor of 2. And this is interesting counting, but it's also interesting technique. As long as you take the ratio of these things, frequently you can have very big numbers and the ratio of probabilities will still come out to be something fairly manageable. I've only got 5 minutes left, but that's fine because I don't really need any of those 5 minutes. So let's cut this tape, take our break, and I will set up the Munchkins for the second half. Okay, we're back on camera. I think tonight might be as good a chance as any for a little bit of introduction. The folks who are watching this on video can't participate, but why don't we just go around the room, give your name, what you do, what, if any, professional relevance this might have, and something else interesting about yourself. So we'll start here.
So I am...
And really speak up loud.
I will try. Excuse me. I am Gene Kaplan. I do market research, and this has some professional and some personal academic relevance.
Oh, when you learn about Simpson's paradox, you'll discover that you'll be an expert on how to lie with statistics. Okay, next.
My name is Owen Callan, and I am just a student, and I'm interested in set theory because it's more interesting than multivariable calculus. I had to do that too. So.
Okay.
I'm Katie Peterson. I homeschool my children.
Jay?
My name is Jay Tucker. I'm taking this course basically for entertainment value, for non-credit. I worked together at Dragon Systems for 5 years with Paul, and we also, I have been a teaching fellow for computer science courses that Paul has taught.
Okay. Continue around.
My name is Ollie Kosart, and I'm actually going to probably be in a computer science PhD program, and this course is recommended as a good starter to get the ball rolling.
Okay.
I'm Kabir Banerjee, and I'm at the CRLS High School, and this is the only math course I've left to take, pretty much.
Oh, okay. Are you going to take Math 138 in the spring?
Which is that?
My geometry course?
No, I've already taken geometry.
Oh, you've taken that one.
And I've taken up through the calculus line up to differential equations.
No, I've got one you haven't taken.
What?
Okay, continuing.
What are we doing?
We're just sort of introducing ourselves.
Oh, I'm Ryan Lane, and why I'm here
Yeah.
is just I thought the class would be interesting, and it's degree credit.
Okay.
Paul Ayers. Take it so I can win World Series of Poker. But like you said, probability is nothing to win. No, I'm just taking it out of pure interest. No other reason. Torture myself, I guess.
Okay.
Sue Kilrain. I have a 35-year-old degree in math and haven't taken a math course since then and wanted to get back into it.
Dana Albrecht, full-time homeschooling dad, was listed as a degree requirement for the...
So this is 2 homeschooling parents in the course, but where are the kids? Aha, okay. I should say, the Extension School is real interested in homeschooling. We've discovered that The number of homeschool students in extension courses has doubled in the last 4 years. And last year, in both the courses I taught, the top student was someone who was being homeschooled. There was actually a 14-year-old in my geometry course who did better than any of the Harvard math concentrators. So in the spring, we're going to have an information session where we're expecting to receive more information than we get about how we can help with homeschooling. Yeah, Jerry?
My name is Jerry Rosen. I'm a retired symphony musician. And I'm taking this course largely because Paul is teaching it. No, that's true. I've taken 2 courses in computer science with him, and I enjoy his courses very much. But I've been interested in this kind of thing. I've played poker and craps and other things pretty much all of my adult life. And I've always wondered how the machinery worked. So now I'm going to find out how to do it right.
Great. Okay.
I'm Benaba Addo, and I'm taking this course because I need to take some more advanced math and find schools in economics.
My name is Emily. I am taking this class because I got an undergraduate degree in math, and I'm trying to decide whether to move on to graduate school.
My name is Catherine Oates. My undergrad and master's degree in engineering, but for the past 2 years I've been living overseas in West Africa, and I'm taking this class to sort of scrape the cobwebs off my brain.
My name is Lynette Glygen, and I'm an analyst for a mortgage bank, and basically just taking the class because I haven't taken a math class in a while.
I'm Anna Vajayan, and I didn't get an undergraduate degree in math, but I'm thinking about either going back to graduate school or trying to find some career that has to do with math because I enjoy it.
Hi, my name is Andrew Singh, and I have a degree in engineering, but I'm just here because I want to, take some classes and make my brain work again.
My name is Patrick, and I'm a degree candidate in math concentration, and I'm a few courses away from exhausting the curriculum, so this is one of the few left I haven't taken.
Okay.
Paul, are you going to post the homework solutions at all? Are you going to get to see them?
I am reluctant to post the homework solution, and let me explain why. I work pretty hard on dreaming up these problems, and some of them are basically one of a kind. So if I give out the solutions, then I can't use them again, and I can't replace them with something equally good. So my hope is that Chris's comments on your papers will tell you enough. We may, on occasion, post comments on problems that people totally botched, but as long as people are mostly getting the problems right, I'm disinclined to post the solutions because that really puts them out where someone can store them on a hard drive, and then the cat's out of the bag.
But we'd probably go and speak to Chris if we just don't get a homework and after the fact and go through it.
Now,
or no.
The homework came back tonight. Emily, are there still some? Yeah, Emily has the remaining papers. So if anyone didn't get homework back, you can get it from Emily. And do you attend section faithfully? Are you willing to take this on? Okay. Sure. So Emily will be the homework delivery person. And any that isn't collected, you can give back to me, and we can try to give back the next week. And I would say, if there is a homework problem where you think an explanation for the whole class would be a good idea, send me an email, and I will write something, and I will ask you please not to, say make and sell an archive of these things. Okay, so the next problem is one of my favorites. This is the Munchkin problem. And the characters involved are my daughter Lisa, my grandson Thomas, and my granddaughter Catherine. And this is a slight simplification of something that actually happened in Logan Airport while we were waiting to fly over to England to meet with my other daughter and her family. The kids got hungry, so Lisa went off to the Dunkin' Donuts stand and bought some Munchkins. Now, I couldn't find Munchkins for sale in Harvard Square, so I had to do with chocolate cookies and plain cookies. So she got 2 chocolate cookies and 4 non-chocolate ones. And having got these cookies, she had the sales clerk put them all into a bag. And then, being a scrupulously fair mom, she reached into her bag and said, Thomas, here's 1, 2, 3 for you, and Catherine, you get the rest. Now, you can see what the situation is. There are a number of ways of permuting the 6 cookies, and Thomas gets the first 3 out of any permutation, and all permutations are deemed equally likely. So let's start out with that. And while I don't want to reproduce the messy formulas from the notes, because I think the symbolic formula is thoroughly unenlightening, and it's the examples that you learn from, I will, for this particular example of Munchkin's, at least use the symbols that are in the general formula. But I would be extremely upset if someone ever did a Munchkin problem on an exam by saying, I remember this awful formula with the 6 different factorials in it, I'm just going to substitute numbers in it. So we've got B equals 4 plain Munchkins, C equals 2 chocolate Munchkins, N equals 3 go into Thomas's bag, and B plus C minus N, which also happens to equal 3, go into Catherine's bag. Now, Thomas is fond of chocolate, and he suffers from attention surplus disorder, and you can sort of see the wheels going round in his head. And my impression that he was thinking, how many chocolate Munchkins have I got? So that's the question we want to answer. Given that these 6 chocolate Munchkins were distributed randomly, 3 into Thomas's bag, 3 into Catherine's, we want to calculate the probability that Thomas has 0 of the chocolate Munchkins, 1 of the chocolate Munchkins, or both of the chocolate Munchkins. And in fact, this is a simpler case of the problem that I solved on the Grand Princess. It turns out there are a host of real-world situations where this analysis works. So let's first count the individual outcomes. How many distinct sets of 3 Munchkins could be in Thomas's bag? Remember, his mother reached into the bag that she got and picked out 3 of these and stuck them in his bag. So the answer is 6 choose 3, which is 6 times 5 times 4 over 3 times 2 times 1, or 5 times 4, or 20. So there are 20 sets of 3 Munchkins, and any of them is equally likely to be in Thomas's bag. So now all Thomas has to figure out is, of these 20 sets of Munchkins, how many include 0 chocolate Munchkins, how many include 1, how many include 2. Let's try first for 0 Munchkins. And we could draw a little diagram like this: plain, 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 chocolate, chocolate, plain. How many different ways are there of Lisa choosing 3 plain Munchkins for Thomas? 4, choose 3. Or if you want to be even simpler, you can say, look, Catherine's got both the chocolate Munchkins. She's got 1 of the 4 plain Munchkins. There are 4 ways that can happen. And the probability that Thomas has 0 is therefore 4 out of 20, or 1/5. Okay, let's try for 1 Munchkin. And the reasoning is always the same. You can look in the notes to see the general reasoning. You ask, how many ways are there of choosing the chocolate munchkins that Thomas has? How many ways are there of choosing his plain munchkins? Multiply them together, divide by this, and you've got the answer. So how many ways of selecting his chocolate munchkin? 2, because there are 2 chocolate munchkins. 2 choose 1. And how many ways of choosing the plain munchkins that went into his bag? 4 choose 2. So that's 2 times 6, or 12. And the probability for 1 munchkin is therefore 12 over 20, or 3/5. Now, my view on probability problems is when you get this close to answering all the possible questions, it's really kind of silly not to do the last case and then check that your probabilities add up to 1. So let's do the 2 Munchkin case. Okay, you could argue this is the same as the first one, except the kids have been interchanged. Or you can start with Thomas. How many ways are there of selecting the 2 chocolate munchkins that he's got? 1, because he's got all of them. And how many ways of selecting his plain munchkin? 4. You can write it as 4 choose 1 if you like. So that's 4. And the probability of 2 munchkins is therefore 4 over 20, or 1/5. And sure enough, these add to 1. Well, 4 choose 1 and 4 choose 3 are equal. You could either say Thomas gets 1 of the 4 munchkins or Catherine gets 3 of the 4 munchkins, and either gives you the same number. So a slightly interesting thing about this, of course, is people who are accustomed to problems involving flipping coins would say, oh, the answer's obvious. There's a 50% chance of 1 munchkin and 25% chance for each of the other 2. And that is not, in fact, the case here. So the answer to this is a little bit counterintuitive. Now, I can't...
I'm sorry.
What?
We have the 1 times 4 1. Could you just say 2 choose 2? Is that accurate?
Yes, it is. Makes for better notes. I'm actually going to change it. Yeah, that explains the methodology of what's going on better. Thank you. We can't do this problem this week, but the rest of the problem goes like this. Catherine reaches into her bag and grabs a munchkin at random and pulls it out, and it's a plain one. And she eats it. And Thomas then says to himself, that means that 1 plain munchkin has been taken out of circulation. Now my odds are a little bit better. Given that that has happened, what's the probability of this case, and this case? But that's a conditional probability, and it will have to wait till next week. This is the original... I need some beverage to go with this. This is the original Munchkin problem. Okay, next one is called the Genoese lottery. This is from Sturzacher. I've never seen it described anywhere else, but it's a fascinating little probability problem. And apparently, a lottery along these lines was actually run in Genoa some centuries back. Sturzacher seems to be very good, in fact, at finding probability problems based on ancient lotteries. My wife does a lot of historical and genealogical research in colonial Rhode Island, and she says, we think of all these straight-laced colonial people and how evil these days that the state raises so much money through the lottery, but in fact in colonial America, lotteries were a very standard way of fundraising and big business for the governments then. So this lottery has sort of cute rules. the deal is this. I've got a complete suit of diamonds here to simulate the case with 13 numbers. But apparently the way this worked was there were numbers 1 through n put into an urn or a barrel or something like that. And then, as happens on TV every night, some of them were drawn out, presumably by some beautiful Genoese maiden. And out they come. Wow, I may actually win. Oh, not quite. And the deal is this. You then arrange these things in order. And you win if you have one run of 3, like this ace-2-3, accompanied by another run of 2 that's separated from it. So if, for example, I had ace-2-3 combined with 8-9, or 9-10, or Jack-Queen, or Queen-King, I would win the lottery. I'd also win if I, say, got a 3-4 combined with a 7-8-9. And looking at this, it may have been devised to be just difficult enough that the average Genoese could not calculate the odds correctly, because it's a slightly messy calculation. So here is the calculation for the Genoese lottery. And to understand this, I actually had to draw some diagrams. So we got 1, 2, 3, on up through 11, 12. And in the example I'm using, the number of cards in the lottery is 13. There are 2 cases, one where the run of 3 is with the lower numbers and the run of 2 with the high numbers, and the other where the run of 2 is lower and the run of 3 is higher. And by symmetry, there are equal number of cases for those 2. Because, for example, if you have ace-2-3 combined with 11-12, you can turn that around and combine 2-3 with the 3 highest cards. So what I want to do is just count the case where the run of 3 is lower, and then I'll double that count. So here's a generic example of that. You might get the 3, 4, and 5, and I'm going to use the symbol K to refer to the lowest number in the run of 3. Now what can happen? Well, you can't have these 2 runs together. 3, 4, 5, 6, 7 doesn't win. The rule says they have to be separated, so there has to be a space here. And the run of 2 might start there, or it might start there. So can you see the run of 2 can either start 2 numbers beyond the highest number in the run of 3, or it can start with number 12. You can have number 12 and number 13. So we can say, given K, the number...
Wait, it can go only at K plus what? 5 then?
Well, it's not, yeah, let's say, so this is K, K plus 1, K plus 2, K plus 3, K plus 4. So it can start anywhere from K plus 4 up to n minus 1. Okay?
Yeah.
So the number of possible runs of 2 is, well, we've got n minus 1, and then what do I subtract from that? It's very easy to do wrong, which is why I want you to think about it. To get the number of possible starting places in here, I take n minus 1 and subtract from it not k plus 4, but k plus 3. And when I do that, I get n minus k minus 4. So the number of ways of having the run of 2 depends on k, and the total number of winning sets with the run of 3 lower is obtained by taking this number, n minus k minus 4, and summing over all the possible values of k. Now, what's the smallest possible value of k?
1.
That's easy. And what's the largest possible value of k?
13 minus.
This is not easy, but if we're going to do it, we might as well do it right. It's 8 in this case, absolutely right, Jerry, and therefore the general formula in terms of n must be
n minus 5.
n minus 5, right? Because you can't start with n, and you have to go 5 numbers beyond that because you have to have 3 and 2 and a gap. So there's the formula, and this looks sort of forbidding, but it's not really as bad as it seems if you make a change of index. I know calculus isn't a requirement for this course, but how many of you happen to have studied at some time integral calculus? Yeah, I was afraid of that. And so you're all familiar with changing variables in an integral, right? Integration by substitution. Well, you can do the same sort of thing with sums. It always strikes people as much harder, though actually the theoretical underpinnings are somewhat easier. So let me show you how this works. This is something that's unfamiliar to people. What I'm going to do is set j equal to n minus k minus 4. And this is like saying, I'm going to set x equals tan 1/2 u. And someone said, why do you do that? Well, I'm just smart and good at this sort of thing. Watch, you'll see it works out. So if you think about it enough, you will realize that this is an appropriate substitution, and you'll see why once you see what happens to the limits. First, one nice feature of this is the quantity that I'm summing is just j. That's a big help. And furthermore, I can say if k is equal to 1, then j is equal to n minus 5, right? N minus 1 minus 4 is n minus 5. If, on the other hand, k is equal to n minus 5, then j is equal to n minus k minus 5 minus 4. Wait a minute. N minus 5 minus 4, which happens to equal 1. So j runs between 1 and n minus 5. And the sum looks like that. Well, this one you may have learned how to do in high school. The best story I've ever heard on this one is kind of like that scene in Monty Python's Life of Brian, where Brian gets the grammar wrong in Romans Go Home and is told to write it 1,000 times on the walls. Gauss was punished in a similar manner. Carl Friedrich Gauss, so the story goes, as a youth of 9 or so, misbehaved in math class, and for punishment was asked by his teacher to add together all the integers between 1 and 1,000 inclusive, and he came up with the answer in a few seconds, of course, because being Gauss, he said, oh yeah, that's easy. For example, 1 and 1,000 add to 1,001, 2 and 999 add to 1,001. There are 500 pairs like that, each sums to 1,001, and therefore the answer is 500 times 1,001, which being Carl Friedrich Gauss, I can do in my head. The teacher could not have been too pleased with this, but the answer turns out to be 1/2 times the upper limit, largest thing you're adding in, times one more than that. And since this is only the case where the run of 3 is lower, if you want the full answer, you have to double that to get without the 1/2. N minus 5 times n minus 4, winning combinations, and therefore the probability of winning this Genoese lottery is n minus 5 times n minus 4 divided by the number of ways of selecting 5 out of your n cards, which is how many? 13, choose 5. Well, it's 10 past 9, which means I'm bound to start trotting out some really messy examples just as people are getting sleepy. And so here's the one I want to do next. This one is called Counting Suit Patterns. This is topic number 8. And this is another very famous counting problem for which the reasoning is not all that widely known. And this is the only simple way that I can think of proving a very important formula that goes by the name of the negative binomial theorem. We're going to be needing that again and again. So here is the problem. Don't eat pecan sandies in class without water. In fact, is there someone who could run out and try to get me a glass of water from somewhere? Thank you, Katie. Okay. Oh, wait a minute.
Hold on, tire.
Oh, wow. Yeah, very raspberry. Okay. So you are a bridge teacher, and you want to give your students practice in bidding a variety of hands. There are actually bridge games you can get on CD or over the internet that allow you to do this sort of thing. And it's kind of more fun to bid when you've got 7-card suits or 2 5-card suits or a suit that you've got no cards in than with a 4-3-3-3 hand. So you might say, I would like to arrange things so that each possible suit pattern is equally likely to come up. And remarkably, there is a way of doing it. My interest is really in counting the number of different suit patterns, but in the process of doing the counting, I'm actually going to exhibit a mechanism that a bridge teacher could use to make each of these come up with equal probability. Now, I've got to be very explicit about what I am and am not doing. When I say suit patterns, the list would look like this. One suit pattern is you've got all 13 spades. That makes for a rather dull game of bridge, though probably good fun. Or 13 hearts. And then in the middle of things, you might have 6 spades, 4 hearts, 3 diamonds. And at the end, you might have 3 spades, 3 hearts, 3 diamonds, 4 clubs. So when I say a suit pattern, I mean that suits are actually associated with the numbers. I believe the problem that would be more interesting to do, 6-4-3-1, 4-3-3-3, counting those, I think there's no closed form solution to that problem. So getting the number of entries on Durango Bill's list is a much harder problem than this. But if you allow yourself to treat 6 spades, 4 hearts, and 3 diamonds as different from 6 hearts, 4 clubs, and 3 diamonds, say, then there's a very clever way of solving the problem, and it works like this. What I do is to take an auxiliary deck. This auxiliary deck consists of all the cards from one suit plus 3 jokers. So it looks like that, and I shuffle it. And I shuffle this so that the 16 cards are in random order, by which I mean any of the 16 factorial permutations is equally likely. But the important thing is the jokers are equally likely to be in any of the positions. Now here's what I do. I start turning over cards until I turn over a joker. Okay? I turned over a joker after 3 diamonds, and I reach into my sorted deck. Oh dear, I shuffled my sorted deck. Oh no, this is not too bad. And I pull out my spade suit, and I say, because I got 3 cards before the first joker, I want to pull out 3 spades. So my hand starts with 3 spades. You with me so far? Now I go back to my auxiliary deck and start turning cards over again. And this time I got 4 cards before I turned over a joker. So I reach into my auxiliary deck again. I grab the heart suit, and out of the heart suit I pick 1, 2, 3, 4 cards. Then I go back here, turn over more of these. And that means I need 5 clubs. So I grab 5 clubs out of my deck, like that. And finally, there's 1 regular card left. And I grab a diamond. Sorry, this isn't all that neat, but you get the idea, right? So what I've done is I have this auxiliary deck with some ordinary cards, X's, and some jokers, J, and it came up like XXXJ, XXXXJ, XXXXJ, X, and my response to that was I put 3 spades, 4 hearts, 5 diamonds, and 1 club into my hand. And can everyone see that every combination of positions for the 3 jokers leads to a different way of distributing the cards among the 4 suits? So if, for example, I wanted 7 spades, 6 hearts, and nothing else, I'd have 7 X's, a joker, 6 X's, and then the remaining jokers at the end. So, remarkably, all we have to count is the number of ways of placing the 3 jokers among the 16 cards in my auxiliary deck. The number of ways to place the 3 jokers is 16. Choose 3. Which is 16 times 15 times 14 over 3 times 2 times 1. And that's the number of ways of getting different suit patterns. When I calculated this, let's see, that gives me an 8. That gives me a 5. So that's 560. If you look at Durango Bill, I think there's something like 39 different suit patterns. And that's reasonable because for each of these, there's somewhere between 4 and 24 ways of assigning different suits to the numbers. And so you end up multiplying by a number that is of the order of 15 or so in order to get this.
But you're saying this is a unique set. Each one of those is unique. You're not going through the...
Yes, it's unique in terms of which suit goes with which number. And that's the easy counting problem. The other one, I'm not a combinatorics expert, but I think the other one is one of these problems that's elementary to state for which no one has ever found a closed form solution. Now, what am I going to do with this? Well, we're going to need the negative binomial theorem, which is much less familiar than the binomial theorem for positive exponent. So I'm now going on to the next topic, which is negative binomial theorem. And I'm going to use this result in order to get the answer. This is a result that is both hard to prove and hard to remember. It's, in fact, incredibly hard to remember. I always put it on the back page of the exam, along with a set of other miscellaneous formulas if it's going to be needed. And I tend to look it up when I need to use it because I'm not sure I've remembered it right. And one student last year said, the formula in the notes disagrees with the formula in the book, disagrees with the formula in this other book. And it turned out they were all right, and there was just different notation used in the three cases. So this is an important but rather messy formula. And the great thing about this proof is that it actually lets you rederive the formula. There's an inductive proof of this, but of course, to do an inductive proof, you have to know what the answer is. All you do is then prove it's correct. Whereas this will let you get the answer even if this will let you both get and prove the answer. So here's how we're going to do it. Here's what we know. We know that 1 minus x raised to the minus 1 power is 1 plus x squared plus x cubed plus dot, dot, dot. I proved that last week by induction for the case where we had a numerator, and then I assumed that x was less than 1 and let n go to infinity. So this is the sum of a geometric series. Here is the geometric series, and here's its sum, 1 over 1 minus x. Now, this looks like a very unpromising way of doing 1 minus x raised to the minus nth power, but let's give it a try. So 1 minus x raised to the minus nth power is equal to the product, write more terms, is equal to the product of n of these factors. So there's the sum of an infinite number of terms. There's another sum of an infinite number of terms. And there's the last sum of the same infinite number of terms. And we're going to multiply them all together. I would say this proof is very much in the style of Euler, who invented much of the theory of infinite series and was a real slob by modern day standards because he hadn't taken calculus. He didn't understand the difference between absolute and conditional convergence. He just happened to be about the greatest mathematician of all times and came up with most of the important formulas by cavalier reasoning, which was basically, if it's true for large n, it's probably true for infinite n too. And there's a suspicion that he tended to check his results numerically before publishing them, because you can't find anything wrong in his books. It's just that his proofs don't stand up frequently by current day standards, since he didn't really understand the subtleties of limits in infinity. But I think this proof would have appealed to him. Multiply together a product of n factors, each of which has an infinite number of terms in it. No problem. All we have to do is ask, what is the coefficient of x raised to the r power? I think by using r, I'm making my notation consistent with the textbooks. So, what are we going to do? Well, of course, what we do is we put jokers between the different factors. You saw what I did with the jokers before. So imagine jokers between the different factors. And here is a typical term when you multiply this out. X squared, you have x and a joker. And then you have x cubed, which is xxx joker. and you have a bunch of other things, and then you have a joker and one more x, and you're done. Everyone take a few seconds to think about this. This is the same problem we just did. Basically, any term that has rx's in it will have these rx's interspersed with jokers that determine how many powers of x come from the first term, the second term, and so on up through the last term. I see lots of puzzled looks.
I'm not following.
Okay, ask a question, Jay.
I'm just not following.
Okay, let me tell you how I went from this to this. Okay, what I'm trying to do is say there are a whole bunch of terms that will lead to x to the r power.
Yes.
And if I can figure out how many of them there are, then I know the coefficient of x to the r. So let's look at a representative term. One way of getting r powers of x is to get 2 powers of x out of this one. That's the xx. And then 3 powers of x out of this one, with the j showing that 2 came from the first and 3 came from the second. And going on, and we have a joker before the last term and then 1 power of x from the last term. So this will be a sequence of symbols which has r x's plus how many jokers? N minus 1. Everyone comfortable with that? Now, you can have any number of x's before the first joker, any number of x's between the first and second jokers, because each of these has all the powers of x, all with a coefficient of 1. So the number of terms contributing is the number of ways of dispersing this many jokers among this many symbols, which is how many choose how many? How many symbols have we got here?
R plus n minus
1. R plus n minus 1. And we choose how many joker positions?
N minus 1.
N minus 1. So there are going to be this many terms, all of which have precisely r x's. Those are the only terms that contribute to x to the r power in this expansion. And there's our answer. I guess I'm going to have to sneak it in here. The answer is 1 minus x raised to the minus n power has terms involving x to the r for all values of r from 0 to infinity. The r equals 0 term is just the one that starts this off. And the coefficient of x to the r is r plus n minus 1, choose n minus 1. And that's the negative binomial expansion. Let me tell you why this is going to be important. A representative probability problem that depends on this. My wife's cousin always said there was a legal principle that every dog gets 1 bite. And it's more interesting if you have the principle that every dog gets 4 bites. So Fido meets up with the postman every day. Fido bites the postman with some small probability. The first 4 times that Fido bites the postman, you get him off. But the 5th time he goes to the pound. And the question is, what is the probability that Fido goes to the pound on precisely the 255th day or something like that? And it turns out that to answer that question, you need something that's called the negative binomial distribution. And the fact that the probabilities involve sum to 1 rests on precisely this series. So I'm going to be pulling this result out later on. Originally, when I thought of teaching this course, having said you don't have to know anything about infinite series, though it would be nice if you knew the geometric series, I thought I'd really have to pull my punches. And then I discovered there's this lovely proof of this. It's in Surzacher also, I believe, that's based on counting arguments I wanted you to learn anyway. Okay, I've got one last topic, and this one it's sort of an anticlimax, but it's the sort of problem I might want to put on the quiz in a couple of weeks, and this was as good a place to sneak it in as any. And it is very much on the subject of counting. So this is counting by inclusion-exclusion. And apropos of a word I just used, anyone here do double cross-sticks? Crossword puzzles? Well, one of the most famous clues of all time, I think this is actually from some famous literary figure, the clue was for God, country, and Yale. And the word turned out to be anticlimax. So, here's my anticlimax. Think about it, folks. Think about it. For God, country, and Yale, anticlimax. Okay, so counting by inclusion-exclusion. This relies on the fact that in proving the inclusion-exclusion formula for probability functions, the only feature of probability functions that I used was that the probability of a disjoint union was the sum of the probabilities. I never used the fact that probabilities could not be negative, and I never used the fact that the probability of the universal event was 1. And there are lots of other things that satisfy this property. In particular, the function n that assigns to any set the number of elements in that set has this property. So does the function that assigns to a set in a Venn diagram its area. And these things are known to mathematicians as finitely additive set functions. Probability functions are one example, but there are many other examples in the world, and the number of elements in the set is probably the simplest of these. So I can say also the number of elements in the union of two disjoint sets is the number of elements in the first set plus the number of elements in the second set if the sets are disjoint. And by using this, I was able to prove for probabilities the inclusion-exclusion formula, and the same proof will work for counting. So if I have two sets that aren't necessarily disjoint, the number of sets in their union is the number of sets in the first one plus the number of sets in the second one. And what's the correction term? Minus the number of sets in the intersection. Thanks, Katie. So what works for probabilities works for sets. And this is the source of lots of brain teasers, questions on aptitude tests, and the like. Here is an example that's a bit politically relevant that I dreamed up for the outline. We've got the Iraqi parliament, and let's say, for the sake of argument, you got 45 Kurds. They form set A. You got 30 women. They form set B. And in this parliament, there are 20 Kurdish women. That's the set A intersect B. And someone says, hey, maybe we can put together a coalition and form a government if we take all the Kurds and all the women. So the question is, how many elements are there in the set A union B? And the answer is, You take 45 Kurds, and you take 30 women, but you've double counted the Kurdish women, so you have to subtract them off, and you get 55. If you want a thoroughly elementary way of seeing this, there's nothing profound about this. You can say, of these 30 women, only 10 are non-Kurdish women, so we are only entitled to add 10 of them onto the Kurds. This becomes a little bit trickier if it's not in this order. If you say, in the Iraqi parliament, there are so many women, there are so many Kurdish women, and the government consists of all the Kurds and all the women, and there are so many members in that coalition. How many Kurds are there in the parliament? And all I'm saying is, if you hit something like this with counting, use inclusion-exclusion just the way you would do for probability, and you'll get the right answer. Okay, next week I'm going to move on to conditional probability, and life is going to get really, really interesting, and we'll do the Monty Hall problem and lots of other classic examples.